right, so last time we started setting up this chart where your function is increasing, your first derivative is positive, and where your function is decreasing, your first derivative is negative. We're going to add on to that a little bit today. So since that's true from here to here, all that exact same information is going to be true from the first derivative to the second derivative, so you can copy it all over again. So increasing, positive, decreasing, negative. And in theory, it would be true for a third derivative and a fourth derivative. Like you could keep repeating that forever. We don't go beyond the second derivative though. There's not a third derivative test. Okay, so like it's going to stop here. But again, in theory, that would just be true forever. Now, what the second derivative tells you about is concavity, which everyone's always like, cavities, is this your teeth? No. Concave, have you ever heard of concave and convex, like what direction it's bending? So if your second derivative is positive, that means your original function is concave up. Negative means concave down. I know that's not real great abbreviation, but that's how it was taught to me, so that's how I've always written it. Main office. All right, so this means concave up, concave down. So concave up is like a smiley face, concave down is like a frowny face. So an inflection point, it's where your second derivative equals 0, but I'm gonna take a minute and talk a little bit about that. So last time we did critical points. That's where your first derivative equaled 0 or was undefined. And period, end of story, those were critical points. You only get an inflection point if there is a change in concavity. So your second derivative could equal 0. That's not a point of inflection unless there's a change. There has to also be a change. So it is a little bit more picky. I'm going to draw some little sketches up here in the margins. If you want to draw them too, you can, just like to show you what this would look like. If you have the original function, so f of x, like this column here, it would be a change in concavity, concave up to concave down or vice versa. That would look something like this. Like this is concave up, and then this is concave down, and that would be your point of inflection. What graph kind of comes to mind? Sine and cosine, they have a lot of inflection points. Do you know what I'm talking about? Like concave up, concave down, because it's a wave, all right? This would not be an example. As if you had concave up and then it changed to linear. That does not count as a change because linear does not have concavity. It's not concave up or concave down. So that does not count. You're probably like, why is she hitting this so hard? Because it showed up on the AP exam once, and I know that my kids probably got it wrong because they would have counted that as an inflection. Now, if you're looking at the first derivative, because a lot of times they'll give you that graph, that would be a change in concavity would be where your first derivative changes from increasing to decreasing or decreasing to increasing, okay? So an example would be something like this. That would be a point of inflection. We change from increasing to decreasing. This would not count as if you have increasing and then it changes to constant. That will not count. Constant is neither increasing nor decreasing, so it does not count. And if they give you the second derivative, which doesn't happen very often, but you can't rule it out, this would be where your second derivative changes from positive to negative or negative to positive. So a change right here. So if your graph did something like this, right there, you've got a point of inflection, change from negative to positive. If it just does this, and again, this is what I was talking about, the second derivative equals 0, but that does not count because there's not a change. Does everyone understand that? Okay, it's come up and that's why I'm like hitting that really hard. All right, so here's your second derivative test. If C is a critical point, so you have to already have determined that you have a critical point. If your second derivative is positive, that means concave up, that would be something like this. That point is the location of a relative minimum. Your graph is concave up, that's going to be a low point. You'll have a relative minimum. If your second derivative is negative means concave down. That would be something like this. And so you would have a what? relative maximum. And if your second derivative is 0, then you get no conclusion. So last class, when it said justify if you have a relative maximum or minimum, you used the first derivative test. From positive to negative was a maximum. From negative to positive was a minimum. Now you have another way that you can justify a relative maximum or relative minimum. It's just like another tool in your toolbox. So we're gonna like totally pull this function apart and list out everything. Find the critical values. How do we do that? Derivative equals 0. Perfect. This is like, do you remember particle motion? When is the particle at rest? We did velocity equals 0. It's exactly that. We're just not calling it velocity. All right, so derivative is 3x squared plus 6x minus 9. We're going to set that equal to 0. Everything will divide by 3. So that'll be x squared plus 2x minus 3 equals 0. You can get away with that because 0 divided by 3 is still 0. And then what's that going to factor into? Yep, good. X plus 3, x minus 1. And so your critical values are -3 and 1. Those are critical points, period, end of story. We set the first derivative equal to 0. Those are our answers. Again, when we get to inflection points, you have to prove that there's a change. All right, increasing and decreasing number lines for each of these. So make a number line for your x plus 3 and a number line for your x minus 1. So x plus 3 is going to change at -3. X minus 1 is going to change at 1. You can pick test numbers to see whether it's positive or negative in each section. But if nothing's backwards, or like if there's not a negative thrown in there or nothing weird has happened, what can you go ahead and put in? Do you remember what symbols plus and minus you can go ahead and put in if it's not like backwards or weird? Okay, then we'll pick test points. That's fine. I didn't know if anybody remembered that. That's fine. Back up a second. Pick a number that lives in this section. -4. -4 plus 3 is negative. Pick a number that lives in this section. 700 plus 3 is positive. All right, now let's do this one. Pick a number that lives in this section. -3 minus 1 is negative. And then pick a number that lives in this section. 15, I like your choices. 15 minus 1 is positive. If there's nothing weird or backwards, you can put in negatives and then positives. They'll all be negative and then turn positive. Vaguely, do you remember that? It just lets you do it a lot faster. All right, so we've sliced up our number line into these 3 sections. The first section, you have a negative times a negative. So that overall sign is positive. In the middle, you have a positive times a negative, so it's negative, and then these are all positive. So now you're going to write your sentences. They will start f of x is or f of x has. Remember, the function you're talking about is f of x. All right. F of x is increasing on what intervals? -infinity to -3 union 1 to infinity. Good, because first derivative is positive there. I almost made it fit. So the function you're talking about is f of x. F prime is like your source that you're citing. Do you know how in English class, when you do like a work cited or like a bibliography, like that's your source you're citing? The first derivative is like your source. He's like your guy that you're quoting. And then I sometimes call this like the sibling statement. F of x is decreasing everywhere else for the opposite reason. All right, so decreasing would be -3 to 1 because first derivative is negative there. And that's what you guys were doing last time. All right, now we're going to talk about relative maximums and minimums. I'm going to verbally do the first derivative test with you, but when we write it down, I'm going to do second derivative test because that's what I want to practice right here. Look at -3. Just watch me point to this. We're just going to have a conversation. At -3, the first derivative changes from positive to negative. So what does that mean? So you would say f of x has a relative maximum at x equals -3 because first derivative changes from positive to negative there. All right. What would the sentence be here at 1? F of x has relative minimum at x equals 1 because f prime changes from negative to positive there. All right, we're going to use the second derivative test though, so that we can practice that. So you can justify it with either test. All right, so let's go back to our first derivative, which is right here. We're going to get the second derivative. Second derivative would be 6x plus 6. And we're going to plug in our critical points, which are -3 and +1. So if you plug in -3 to that, what are you going to get? -12. And if you plug in 1, 12, that's kind of interesting. 1 is -12, 1's +12. It actually doesn't matter what the number is. We're just looking at positive or negative, right? So f of x has, remember that's how you want to start your statement. F of x has a relative maximum at x equals -3 because, and then there's two things you have to say. First, you have to show that it is a critical point. So the way that we do that is because the first derivative at -3 is 0. That says that it's a critical point. And the second derivative at -3 is negative. That means concave down. And again, if your graph is concave down, you end up with a maximum. Like just minding it with my body. Like this would be the graph, you have a maximum. All right, so then your sibling statement. F of x has a relative minimum at x equals 1 because, and again, there's two things you have to say. You have to say that it's a critical point. So how would we say that? Because what? Perfect. Awesome. If it's a critical point and your graph is concave up, you end up with a relative minimum. All right, letter D. Find the absolute extrema. That's your candidates test. So you're going to make a chart, plug into the original function. Who are the candidates? And I'm not looking for a number. I'm looking for like what, like how do you get your candidates? They come from what? Endpoints and critical points. All right, so our endpoints, those are given in the problem, -4 and 0. And then our critical point is -3. We also had a critical point at 1, but why did I not put that on there? Yeah, it's past 0. It's outside of the interval, so I didn't test 1. So these get plugged into the original function, which is all the way back up here. All right, buckle up, here we go. -4 cubed. Good, -64. All right, -4 squared would be 16 times 3 is 48. And then -4 times -9 would be 36, and then +4. Sometimes you have to do stuff like this without a calculator. It's a mess. But let's see, 36 and 4 is 40. Plus 48 would be 88. 88 minus 64 would be 24. There, we survived. All right, -3, plugging that in. -3 cubed, -27. -3 squared would be 9 times 3 would be 27. So that's really convenient. -9 times -3 is 27. That's a lot of 27s. I didn't do that wrong in my head, did I? A lot of 27s. All right, and then +4. All right, so these two cancel, and that'll be 31. And then you catch a break here. You're like, oh, thank goodness. Because if you plug in 0, it's just going to be 4. Do you ever like need to catch a break and you finally catch a break? It's like, oh, thank goodness, right? So the absolute maximum is, and then it's just whatever's the biggest number you got, which was 31 at x equals -3. And the absolute minimum is 4 at x equals 0. The justification is the chart. You don't have to put a because statement. Like, this is your justification. You tested every candidate and showed what they came out to. All right, inflection points. That's second derivative equals 0, and you have to show that there's a change. So what was our second derivative? We already found that on here, didn't we? Yeah, 6x plus 6 equals 0. So if you solve that, what are you going to get for x? Yeah, -1, right? And when you do critical points, that would just be the answer. When it is an inflection point, you have to also test, is there a change? So let's pick a number in this section. -4. If you plug in -4 to this, you'll have -24 plus 6. That's negative. If you pick a number in this section, 83 times 6, I don't know what that is, plus 6, but I know it's going to be positive. Again, if nothing strange happened, it's going to be negative and then turn positive. So is there a change? Yes. And so that is, in fact, an inflection point. So if you want a statement, it would be f of x has, you always want to start with f of x is or f of x has. An inflection point at x equals -1 because second derivative changes from negative to positive there. If they ask for a justification, where is there an inflection point and justify, then you would. Typically, like what I've seen, the way they do these on the free response part, because if it's on the multiple choice part, you don't have to justify, right? You just have to pick A, B, C, D. If it's on the free response part, the way I've seen it most often is that they give you a graph of the first derivative, and it's like this. So I threw one of these on the back of here. This is how I've seen it more often, but that is how you would write it out for sake of being thorough. All right, and then concave up, concave down, and then we'll do a little break here. We already made the number line. Here's where the graph is, the second derivative is negative. That means the graph is concave down. So f of x is, I can't stress that enough. Start your sentence with f of x is or f of x has. That's like the noun of your sentence. F of x is concave down, -infinity to -1 because now the second derivative is like your source that you're citing there. He's like your bibliography. The second derivative is negative there. And then the sibling statement, f of x is concave up, -1 to infinity, because second derivative is positive there. All right, so for this one, they give us a graph instead of a function, which I know easy and difficult is always an opinion, but I find these easier because you don't have to actually do any like working it out. You're just going to look at the graph. And I put this on a sticky note, and I'm just going to keep this here by the projector and pull it out. You probably want to put this on a sticky note too, so you don't have to recopy this onto the top of every single piece of paper. This is so useful, and there's so much information on it right there. I'm just going to pull that out and keep my sticky note here. Okay? So this is the graph of what? Be really careful. The derivative. Oftentimes, that is the one that they're going to give you. So this is the graph that we're looking at. Defined from -4 to 4. They give us this f of 3 equals 8. That'll come up at some point, all right? And we don't need to give a full coordinate, just the x value. All right, on what interval is f decreasing? All right, look at the sticky note. Decreasing is where the derivative is what? Negative. You're looking at the derivative. Where is this graph negative? From where to where? Yeah, now they capped it at -4. So it'll be -4 to -3, but yeah, this section right here. So from -4 to -3. Critical points. That's, oh, you guys can't see that sticky note at all. I don't know that I can make it much darker without having it be completely washed out. Oh, that's a bummer. All right, guess you guys just have to know it. You can flip your paper over, it's on the other side. Or like I said, make yourself a sticky note, all right? Critical numbers, that's where the derivative equals 0. You're looking at the derivative, so where does this derivative equal 0? Yep, -3 and 3. All right, local, that means relative minimum. That's where the derivative changes from what to what. Minimum means from what to what. Good, that's from below to above. So where does that happen? -3, here's where we have a change from negative to positive, -3. Concave down, all right, maybe I can hold, oh look, I'll just hold it closer to the screen. All right, concave down is where the derivative is decreasing. Can you guys see it better there? Sort of. That's so funny, when I'm looking at it right here, it's perfect. Then on the projector, it's all blurry. All right, concave down is where the derivative is decreasing. You're looking at the derivative, so where is this graph decreasing? Yeah, -1 to 3. Point of inflection. All right, a point of inflection means a change in concavity. That's where the first derivative changes from increasing to decreasing or decreasing to increasing. You actually have to have a change. All right, so there's 2 places that happens. Where are they? Yep, -1 and 3. This next question is really weird. I've thought about deleting it off of here, but I don't want to get rid of weird questions. Where do we have a maximum from -2 to 2? All right, look, here's -2, which is right here. Here's +2 right here. The derivative is above sea level for that entire time. The derivative is positive for that entire interval. So if the derivative is positive, what does that mean your graph's doing? So if the graph increases for that entire time, where's the maximum? The end of it, right? Like if it increases the whole time, the maximum is going to be when you get to the end of the interval. So that would be +2. That's a weird question, but I kind of like it. Like if it increases all the time, then the maximum's at the end. All right, and then this one wants an equation. What 2 things do you need to write an equation? Slope and weight. All right, our point of tangent C is 3. Oh, hey, they told us that back in the beginning of the problem. It's 0.3 comma what? 8. That's where that came up. And then slope comes from the derivative. So we want the derivative at 3. This is your derivative graph. At 3, what is the value? 0, which is kind of weird because then your slope is 0. So it would be y - 8 equals 0, x - 3. If you wanted to simplify that down, this entire thing is just nothing. Oh, it's a +3. Okay, but you're right. If it was a -3, then it would be plus. Yeah, so if you wanted to like simplify that down, you could just put y equals 8. I like to write out the whole thing. That's me. I kind of like these ones too. All the information's given in a table. It's easier when they give you the information in a table or a graph because you kind of don't have to do any math. You don't like this was a lot of work, wasn't it? Like here, it's less work, so it's nice. All right, I would do the graph first. I know that's part F, but I would do the graph first. These are the points that we're going to plot, the f of x points. So you can plot 0, 0, 1, -2, 2, 0, and 3, 3. Looks like a little constellation. Now you don't need to worry about the first derivative. The first derivative tells you about increasing and decreasing. The reason you don't have to worry about that is you can't connect these points without decreasing and then increasing. Like it's just going to happen. So you don't have to worry about it. The only thing you have to worry about is concavity. So look at the line for second derivative. The second derivative is positive. That means concave up. And then it's positive, which is concave up. And then it's still positive. So you want to connect them and just be concave up the entire time. So here's concave up, and then it's going to stay being concave up. It looks kind of like a cloud or something. But you want it to be bending upwards the entire time. So hey, look, sharp edge. Does that make sense with what's given in the table? Yeah, it says does not exist there. You don't get derivatives there because of the sharp edge. So I would do the graph and then you can use it to answer the question. Absolute maximum. That's this point right here. So that would be 3 at x equals 3. All right, absolute minimum, that would be this point all the way down here. So -2 at x equals 1. Now the relative ones, you can have a point that's both relative and absolute maximum or minimum. The thing is the relative ones cannot be endpoints because an endpoint is not relative to something else. So the relative ones just can't be endpoints. And we might not have any. I think one of these might be none. Relative maximum, we are not going to have one. The graph never goes up and comes back down. So we don't see that happen anywhere. Relative minimum is going to be what? Because there is one of those. Yeah, it's the same. Good. It's the same as the maximum, -2 at x equals 1. And then inflection points, that's a change in concavity. Well, this graph never changes concavity. It's concave up all the time. So there isn't one. Yeah, so that's a good question. Since there has to be a change from positive to negative or negative to positive, it can't be an endpoint. So actually, let me just elongate that a little bit. That couldn't be an endpoint either because there has to be a change. Yes, that is a good point. All right, sketch a graph. Oh, I put one like this on the bonus of one of your tests. Do you remember that? Like, I think it was the limit one, the first test. I was like, do all that stuff. Okay. Vertical asymptote at x equals 1. Yeah, this one's actually easier than that one. It just involves a derivative, so that's the only thing. Horizontal asymptote at y equals 2. And remember, horizontal asymptotes are only at the edges, not the whole way through. It's just the end behavior. Then we're told first derivative is negative. All right, if your first derivative is negative, what does that mean your function is doing? I'm holding the stick-it note up here if you can sort of see it. First derivative is negative. Decreasing, perfect. So we want to be decreasing for everything smaller than 1. So that would be something like this. And then it says first derivative is positive. That means increasing. So we want to be increasing after 1. So that would be something like this. All right, number 5 is written out 2 ways. We have the function written out like this and factored, which is nice because sometimes you can look at one version, sometimes you can look at the other. A says find the roots. That's where this would equal 0. So the factored version is a little bit easier to look at there. What would be our roots? X equals what? Good, -1 and 2. And we're going to draw a graph. So you may as well go ahead and put those on it. The roots means x-intercept, your 0. So right there and right there. Critical points, that's derivative equals 0. All right, so what is our derivative? I would look at this version of it this time. 3x squared minus 6x, perfect. Set it equal to 0. And so what can we factor out? Right, 3x, you'll be left with x minus 2. And if you set those equal to 0, you're going to get 0 and 2. You don't have to check if there's a change. Those are critical points, period, end of story. Right, it's the inflection points where it's a little bit more picky. All right, relative extrema. Let me make a number line for 3x and x minus 2. So 3x is going to change at 0. X minus 2 is going to change at 2. they're going to be negative and then turn positive. The only time it won't be negative and then turn positive is, for example, if you had something squared, like say it was x minus 3 squared. Squared means what? Yeah, like that would be positive the whole way across. Or if you had something backwards, like instead of an x minus 2, if it was a 2 minus x, do you get what I'm saying? Like instead of negative to positive, that one would be positive to negative. But if nothing's weird, like, and if something weird happened, you would know because you'd be like, huh, that was weird. Otherwise, it's going to be negative and then turn positive. So that kind of allows you to fill it in quicker. So the overall sign will be what? Positive, negative, positive. All right, so what's going on at 0? Maximum or minimum? Maximum. Positive to negative means maximum. So our relative maximum is not 0, it's at 0. In order to get the value, you would have to plug 0 back in to the original function. So if you plug in 0, what are you going to get? 4. Good. So relative maximum is 4 at x equals 0, and you can go ahead and plot that. Because the point is we're trying to put a graph together. And then your relative minimum is not 2, it's at 2. So you'd have to plug 2 back in. If you plug in 2, you're going to get 0 though. If you look right here, 2 minus 2 would be 0. We already have that on the graph. So 0 at x equals 2. That's going to be this point. We already have it plotted. All right, how do you get a point of inflection? Perfect, second derivative. So look back at your first derivative. It's in part B, it's right here. Second derivative would be, good, 6x minus 6, set it equal to 0. X would be 1. It's not an inflection point unless there's a change. But spoiler alert, it's gonna change from negative to positive. So 1 is the location of the inflection point. If you want to be able to plot that on here, you have to plug 1 back in. So if we plug 1 in, let's see, that'll be 1 minus 3. So negative 2 plus 4 would be 2. So we get the point 1, 2. So it looks like a little constellation. You're going to connect them. Just follow along with the concavity. Look, I put the number line here. Negative means concave down, and then positive concave up. So, and the change is going to happen at 1. So we want to be concave down until we get to 1. And then concave up after that. I tried to make mine like as dramatic as possible to see the bend of the graph. That's a cute little graph. All right, we'll do number 6 and then do another break. A differentiable function has the following information. F of 3 equals 7. All right, all that tells us is that the 0.37 is on the graph. F of 3 equals 7 just means you have the 0.37. That's all that tells us. The derivative of 3 is 0. Now that's a little bit more informative. What does that tell us? It's a critical point. Good. If your derivative equals 0, that means critical point. And then they tell us the second derivative at 3 is negative 4. It doesn't matter so much that it's negative 4. What's important there is that it's negative. If your second derivative is negative, what does that mean? Concave down. And I usually just draw a picture of it. I'm a visual person. I need the picture. Concave down would look like that. So what conclusion can you draw about that point? It is a, what kind of maximum? Relative maximum. All right, so your relative maximum is 7 at x equals 3. All right, so I'm just going to say this. I already did, but I want to say it so that it's on the recording. we have the graph of f prime. So just be aware of what you're looking at. And this is going to be hard for me to shuffle this up and down here because to write and see the graph. Oh, I'm sorry. Thank you. All right, there we go. All right. On what intervals is the function f of x, which is not this one? Okay, you're answering questions about a graph you're not looking at. Increasing, that's where the derivative is positive. That's above sea level. So that would be from -8 to -6, and then also 9.5 to 10. Decreasing would be, or no, from take 2. Let me just back up. That's where the derivative is above sea level. So -8 to -6, union -2 to 9.5. There, is that better? I'm sorry. I'm a human, I made a mistake. All right. Decreasing would be below sea level. So that would be from -6 to -2, and then 9.5 to 10. Got ahead of myself there. All right, concave up is where the derivative is increasing. So that would be from -4 to 2, this section here. And then also 4 to 7. Concave down would be where the derivative is decreasing. So -8 to -4, and then 2 to 4, and then 7 to 10. No one yelled at me, so I'm assuming you all get it. Okay, good. We're gonna look after each other. All right, local maximum, that would be where the derivative changes from positive to negative. So that happens at -6, we go from above to below, and then at 9.5. Local minimum, relative minimum, would be a change from negative to positive. So that would be at -2. At not at -4, at +4, this is a critical point, but not the location of a relative maximum or minimum, but it's still a critical point. We good there? Okay. Points of inflection. That's where your derivative changes from increasing to decreasing or decreasing to increasing. That's the one where it's a long sentence to justify it. There's going to be a lot of them. We've got -4. This doesn't count. I think I hit that hard enough. All right. 2, 4, and 7. There are a lot of inflection points on that. All right, average rate of change. What does an average rate of change mean? Slope from -6 to 3. So we have the point -6, 0, and you guys jumped on that answer, which makes me happy. 3, 1. All right, so it would be 1 minus 0 over 3 plus 6. You can leave it like that, but I'm just going to go ahead and simplify it. 1/9. Letter B, does mean value theorem guarantee a value of C on that interval where the second derivative is equal to this average rate of change? And you guys, I heard you guys talking about it. The answer is no. Why not? Good. Not differentiable at where? Yeah, x equals -1 and 2 due to sharp edges. I abbreviated differentiable. Is there such a value of C? Now what that's asking is, the theorem doesn't guarantee it, but there still might be, even if it's not guaranteed, just, by happen chance, there might be one. So we're looking for, is there going to be a slope of 1/9, a tangent line with a slope of 1/9 somewhere on this interval -6 to 3? I'm going to attempt to draw this as well as I can. Here's -6, 0, here's 3, 1. We're connecting those with our slope of 1/9. So what the question's asking is, even though it's not guaranteed, could we find somewhere in that interval where we do get a tangent line that's parallel to that? And yeah, it's going to happen like here-ish. Do you see if I draw in a tangent line that just comes by and kisses the graph at that one point? You see how they would be parallel? I'm not a great artist, but are you following me here? Like, okay. So yes, even though it's not guaranteed, there will be one. And I'm just going to say between, what would it be between? I'm even going to say between -4 and -3. You're not wrong, but just to like narrow it down a little bit further, it would be in there somewhere. So between x equals -4 and x equals -3. So even though it wasn't guaranteed, we still ended up with 1.